Hello and welcome to this third in the series of 6 films about kinetic theory. This one deals with gases and so does the next one. This one really just gets us to think about how the gas particles behave and about some assumptions that we make to do with those particles. The next film will concern itself more about how the properties of gases will change depending on the conditions that they're subjected to. Okay, so we are going to look at the assumptions that we make about gas particles to help us explain gas behavior. Okay, these aren't quite, they don't really make sense, but they're convenient approximations that we make so that we can predict with a relative amount of ease how gases will behave. Okay, they are kind of nonsensical at the limits or at the extremes of conditions, but under most conditions they work extremely well. Okay, and we're also going to have a look carefully at how graphs can show us, right, this is really quite an important thing as well, okay, these graphs that show how the temperature of gases is related to the average kinetic energy of particles in a gas. Okay, we shall start off by looking at the ideal gas assumptions. Okay, these are things that we have to assume about gas particles if we're going to make, if our attempts at describing gases and doing calculations with gases are going to be relatively straightforward. As I say, these things work quite well in the kind of, in the range of conditions that we usually encounter. They don't work very well at the very extremes of temperature and pressure, but that's okay because we don't normally encounter them. Okay? So, when we are talking about a so-called ideal gas, right, so it's just a notional gas, all right, that we can do calculations with easily, we assume that the particles themselves occupy no space, okay? We'll see later why that's important, all right, but clearly it makes no sense. How can things that are there not occupy any space, all right? It's an assumption that we make because they occupy so little space that we can basically ignore it. Okay, we make the assumption that there are no attractions at all between particles. So two particles that fly past each other and come very close don't experience any attraction to one another. This is important when the particles start getting quite close together. All right, those attractions will start to become quite significant, but when they're far apart, like most gases are, that's not a problem at all. We assume that any collisions are perfectly elastic, which means that no energy is lost in a collision. That is something that, again, makes no sense in terms of classical physics. And we, very, very importantly, assume that the average kinetic energy of particles in a sample will define the temperature of that sample. Okay, I can't really overemphasize how important that point is in terms of this topic. Okay, here is something called an energy distribution curve. I'm going to go quite quickly through this because I know you can stop this film as many times as you like, okay, but this is an important graph and it's important to understand what it shows. Right, we've got some labels on it, okay, this is prob, right, this refers to the probability of finding a particle with a certain kinetic energy. So one way of picturing this is as if I don't know, you're flying around in a sample of a gas in a particle-sized spaceship, and every time you see a particle, you park your spaceship next to it. I don't know, you get out your energy measuring device and you measure its energy. Okay, so as you go along and you go, right, I've come back to my base and I've got out of my spaceship and I've looked at, okay, how many particles did I find with this energy? Oh, none. Okay, so this is a really important point of the graph. We never find any particles with no energy. Okay, this means that no particles are ever completely motionless. That's really important. Okay, as the kinetic energy goes up, it becomes more and more likely that you will find particles with those energies until you reach a peak. Okay, and notice that the peaks for these three lines are in different places. Okay, so in other words, the most popular energy of a particle at 100 degrees is more popular than that at 25 degrees, which is more popular than that at 0. Okay, but you can see that under all these, for all these three temperatures, we get particles with very high energies. right? So there are particles at 0 degrees that have higher energies than some of the particles at 100 degrees, okay? All this graph shows is that as the temperature increases, so the probability of molecules having higher energy increases. In other words, the average temperature or the average kinetic energy increases as the temperature increases. Okay? That's not to say that all particles have more energy when they're hotter. Okay? We get some particles that have extreme energies compared to their temperatures. We have some particles that have very, very low energies compared to their temperature. Okay? The average is what we are looking for. Okay? It's the average that increases as the temperature rises. So that is something called an energy distribution curve, sometimes called a Boltzmann distribution, by the way. Okay? And it shows how the energies of particles are distributed amongst those particles in the sample. Okay? So in other words, it's like a probability curve. Okay? It's like you've conducted a survey of all the particles and said how popular is each energy. Now, what is this supposed to be showing us? Right, okay, well, let's have a look at the axes on the graph, I suppose. That makes sense. Right, this axis is now not energy, but speed. Okay? Speed in the expression for kinetic energy is here. Strictly speaking, it's velocity. Okay, not speed. A physicist would tell me off for calling that speed. Okay, it's velocity. But this, I suppose this ignores the direction of these speeds and it just measures their speed, literally, okay, and the probability density. This time we've got 4 different gases, but they're all at the same temperature, okay? Now look, helium, with its fairly light atoms, has quite a high average speed, okay? Xenon, with its heavy particles, has quite a low average speed, all right? Now why is that? Well, they're all the same temperature. So they've all got the same average kinetic energy in these samples. But kinetic energy is equal to half mv squared. So if you've got the same kinetic energy as something else, but your mass is small, like helium, then you must have a very high speed to make up for it. Otherwise your kinetic energy will be small. If you've got a very low speed, but your kinetic energy is the same as something else because your temperatures are the same, like xenon here, same temperature as the helium but has a lower speed. Well, why is that? Well, because xenon's mass is bigger. So its speed has to be lower if its kinetic energy is going to be the same. All right? So that's really quite an important slide about how the speed of particles is related to their kinetic energy and to their mass. All right? And it all comes down to this formula here, which if you do physics, then I'm sure you're extremely familiar with by now. Okay, I've reached the end of the slideshow, and once again, it was a slideshow that didn't have a lot of slides, but had an awful lot of key points in it. Okay, so can I recommend that you go back and watch it again and just check that you've got those key points in your notes. If you feel like you have, then the next presentation is about gas laws, I believe. It's the 4th one.